All right, let's get started. So we have been discussing MOSFETs and MOSFET-based circuits. Today we'll look at a few examples of how to bias these different MOSFET-based circuits and what we exactly mean by biasing, as well as we'll start our discussions on MOSFET-based amplifiers. But before that, I'd like to make one announcement that according to your syllabus, you already know that there is a test on October 25th, that is next Wednesday. So I think around 9 days from now. In this test, again, the syllabus will be diodes as well as regarding MOSFETs, whatever we'll be discussing till Wednesday's lecture. Okay, so the DC biasing of MOSFETs and the physics of MOSFET, that will be included in test 2. Okay. All right. So let's go back to our discussions. So we have looked into all these different properties of the MOSFET already that, okay, there are two different regions of where this MOSFET can operate. One is called the triode region or the linear region. The other one is called the saturation region. And we have also looked into these two different cases that the equations for the MOSFET in triode and the equation for MOSFET in saturation are also very different. So for example, this is the equation of current when the MOSFET is in triode region. And this is the equation of the MOSFET when it is in the saturation or active region. Okay. Now, when we'll be using the MOSFET as an amplifier, we'll be mostly interested in the saturation region. So out of these two equations, this is the equation which will be more important to you because this is the equation when the MOSFET is in saturation or in active region. And only if the MOSFET is in active region, you can expect a gain out of it. We have also looked into the explanation that why do we expect a gain out of the MOSFET when it is in saturation? And why do you not expect a gain out of the MOSFET when it is in triode or in cutoff region? And that basically boils down to your voltage transfer characteristics or VTC. So all right, so you already know about the voltage transfer characteristic from your discussions regarding op-amp. But here also in the previous lecture, we have looked into why this VTC should look like this when you have a MOSFET-based amplifier. And we haven't really discussed about the equations for amplification, that what is the gain for this MOSFET amplifier. But we have discussed the VTC and what the VTC should look like. And from this curve, you already know that if the slope of the VTC is more in any region, then you can expect a positive gain out of it. Because again, just from the graphical representation that we had gone through in the previous lecture, you'll know that if your input varies by a small amount, if your slope is high, your output will vary by a larger amount. If your slope is more than 1. If your slope is less than 1, you'll get a gain less than 1. So all you need now is that a region where your slope is more than 1. And we have already mentioned this in a hand-wavy manner at this stage that, okay, in your saturation region, your gain will be more than 1, whereas in triode region or cutoff region, your gain will be less than 1. Cutoff region is very easy to understand. Your output does not change at all, even if your input changes. Even if your VGS or the gate to source voltage keeps on increasing, the output does not change at all, which means that you have a zero slope in the cutoff region, which means you'll have a zero gain in the cutoff region, right? But your linear region or the triode region, which is here, and your saturation region, which is here, will both result in some amount of gain. We'll look into what are the equations of those gains in the saturation and triode regions, and we'll prove that the gain in your saturation or active region will be more than 1. Okay, so these are the details that we have already gone through. We have looked into what would be the equation for transconductance. That is, if you have a VGS in your x-axis and you have ID in your y-axis, that is the gain current, GM or transconductance is the AC current divided by the AC voltage. So if you are applying an AC voltage, if you are applying a small amount of change in voltage at your input, what is the amount of change do you expect at your output in terms of current? That's what transconductance means. It's a conductance quantity because your input is voltage, your output is current. And that's true for any kind of MOSFET. That you apply a gate voltage there cannot be any kind of gate current, because as you know that the gate will have an oxide layer, and there cannot be any current flowing through an insulator, right? There cannot be any current flowing through plastic or silicon dioxide, right? So because this is an insulator layer, there cannot be any current going into the gate of the MOSFET. So you can only apply a voltage at the gate of the MOSFET, but because of that application of the voltage, you will create a current through the MOSFET. That's how the device actually operates. And we have looked into the device physics, that why do you see a flow of current from drain to source for an N-channel MOSFET. So GM is basically your AC current divided by AC voltage, or you can say that that's the change in current divided by the change in voltage, or the derivative of your ID current with respect to the VGS voltage. And you already know your equations of ID with respect to your VGS. These are your two equations. So you can find out what would be your GM in the triode region and what would be your GM in the active or saturation region, just by taking a derivative of your ID current with respect to the VGS voltage. Okay. So that would be your GM when you take that derivative. Okay. Now we have also looked into this, that GM can be represented in three different forms. One is K times VOV, where K is the device transconductance, which is equal to the process transconductance K prime multiplied with the device's aspect ratio W over L. So K multiplied with overdrive, that can give you GM. Square root of 2 times K times ID, that also gives you GM. And twice ID divided by VOV, that also gives you GM. Now, what is the equation that you'll use in your let's say in your homework problem or in your exam, if you see these kind of equations coming in? If you are given the value of, let's say, the aspect ratio, the device transconductance and overdrive, you can use this equation. But let's say your overdrive voltage is not given, instead your current is given. So you can use the second equation, correct? You already have your W over L, and instead of V overdrive, if you are given the ID to be a constant, then you can use the second equation. If your W over L is not given, if that is something you are trying to find out, but your ID and VOV are given, then you can use the third equation. So it depends on what are the quantities that are given. So there are three quantities that can change. One is the aspect ratio, one is the gate overdrive voltage, and one is the current through the MOSFET. Any two out of these three could be given, and you can find out your GM or transconductance as the function of those two quantities. Okay. All right. So now the big question, that what would be your gain? Okay. What would be your gain in this particular example that we had already looked into? That, okay, you have a MOSFET, you're applying an AC voltage as well as a DC voltage at the gate. Now, why are you applying a DC voltage? That is to make sure that you bias the MOSFET correctly. What is meant by biasing? Again, go back to your VTC. This is your V in, this is your V out. Biasing the MOSFET means that you have to start at a point, you have to start at a voltage where you can expect some amount of gain. If you start here, you don't expect any gain here. If you start here, again, you don't expect any gain over here. But let's say at this point where you are kind of at the middle of the rail, yeah, if your supply rail is VDD and your ground is VSS, at the middle of your VDD and VSS, you can expect some amount of gain. That is at the middle of your VTC curve, voltage transfer characteristic curve. So you have to start at a point where you can expect some amount of gain. If you start somewhere else, you'll not get any kind of gain. And that is the meaning of bias. That, okay, if you're trying to operate a steam engine, if you're trying to create steam out of water, you have to be at 100 degrees centigrade or 212 degrees Fahrenheit. You cannot expect the steam to generate if you are at 30 degrees centigrade, right? That's the meaning of biasing, that you have to put your environment at certain condition so that you can expect the transistor to do whatever you want it to do, right? In this case, you want the transistor to have some amount of gain, and for that, you have to bias it at a point where you do expect gain. Okay, so that's the reason why you have this DC voltage over here. And now on top of that DC voltage, if you have a small AC voltage at your input, you'll see a large amount of AC voltage at your output, provided that you have a large amount of gain. So what is the value of the gain that you can expect in this case? You already know that your gain, AV, right? A substitute V is your voltage gain, voltage amplification. So that would be your output voltage divided by input voltage, just from your equations that you have learned during when we were studying op amps, right? Your output voltage divided by your input voltage is your voltage gain. Now, your input voltage is VGS, the small signal VGS or the AC VGS, that's your input voltage. Remember, when we were talking about gain, we are again talking about only the AC quantities. You do not have a DC voltage gain. You cannot expect a DC voltage of 1 volt to be applied at the input, and you do not expect a DC voltage gain at the output. Whenever we are talking about gain, we are talking about AC voltage gain. So you apply, when assuming that you have biased the device correctly, if you apply, let's say 10 millivolt AC, a 10 millivolt sine wave at your input, you'll expect that you probably get a 100 millivolt sine wave at the output. That's the definition of gain. Okay, so when you are talking about gain, you are always talking about AC quantities or small signal quantities, that you have a small input and you expect a little bit larger output if your gain is more than 1. All right, so your AC voltage, VGS, is your input. What is your output? Your output is the drain to source voltage across the MOSFET. So if you are taking the voltage across at this point, this is your ground. So what is the output voltage? Output voltage is whatever voltage that you apply across these 2 points, or whatever voltage that you see across these 2 points, which is nothing but your drain to source voltage of the MOSFET. Now, what is the drain to source voltage of the MOSFET? That would be given by the drain current of the MOSFET multiplied with the load that you see at the output point, because voltage is current multiplied with resistance. That's Ohm's law. And we'll prove this in a minute, that your VDS will be equal to minus of ID times RD. So we'll prove this in a minute, but let's say for now, we assume that your VDS, the output voltage, is equal to the current that is flowing through the terminal multiplied with this resistance that you have applied at the drain terminal. And we'll prove this, that why it is true. Okay, so if your GM is equal to ID divided by VGS, small signal ID divided by small signal VGS, then what is your voltage gain? Your voltage gain was VDS over VGS, and you know that VDS is equal to minus ID times RD. And you also know that RD divided by VGS, that is this quantity. Let me take a different color. So your ID divided by VGS, that is equal to your GM. So your voltage gain becomes minus GM times RD. So that's your voltage gain eventually. And it's very easy to understand all the other quantities, but probably what you don't understand at this point is that why my VDS is equal to minus ID times RD. We'll prove that in a minute. But apart from that, everything else should be clear, that your voltage gain is equal to output voltage divided by input voltage. And if you assume that your output voltage is equal to minus ID times RD, you can represent your GM, or you already know your GM to be ID divided by VGS. So you can write your AV, your voltage gain, to be minus GM times RD. And in terms of the units, it makes sense because your GM is a transconductance, so that is a current divided by a voltage. Now you multiply that with resistance, so your current gets multiplied with the resistance, so that becomes a voltage. So eventually you have a voltage over voltage quantity, and you're trying to find out the voltage gain. So this makes sense. Transconductance multiplied with the resistance gives you a voltage gain, right? Because it will be voltage at the numerator and voltage at the denominator. Okay. Now let's see, did we say that my output voltage VDS is equal to minus ID times RD? For that, we draw a AC small signal model. So this is similar to the linear equivalent model that you had for the op amps. That the way the linear equivalent model or the AC small signal model is drawn for a MOSFET is that you have a gate terminal, you have a source terminal, and you have a drain terminal, right? These are the 3 terminals you have. At the gate terminal, you will apply your input, your VGS, that's your AC input voltage. That is applied across the gate terminal with respect to the source terminal. And remember that the source for the NMOS device is grounded in most scenarios that we'll encounter in this course. So if your source is the reference point or the common point, and at the gate you're applying your input, you will see you'll observe your output at the drain terminal. the way it is, the small signal model for the MOSFET is represented is this, that if you apply a gate to source voltage between the gate terminal and source terminal, then between the drain terminal and the source terminal, you'll see a current. And the current will flow from drain to source, right? Because for an NMOS device, current flows from drain to source. The majority carriers, which are electrons, they flow from source to drain, which means the current will flow in the opposite direction, which is drain to source. That's the direction of this current. And the amount of current is basically transconductance multiplied with input voltage. Right? Transconductance is current over voltage, conductance is current over voltage. So current over voltage multiplied with voltage gives you a current. So this is your output current. The drain to source current is given by this dependent current source. And as you see that this is now very similar to your op-amp small signal model or the linear equivalent model of the op-amp, where we assume that if it is a transconductance, the transconductance multiplied with the input voltage gives you the output current for the op-amp. It's the same thing, nothing different here. Okay. One other thing that needs to be taken into consideration here is that this is the way you represent an ideal current source. But in reality, there is no ideal current source. All current sources are non-ideal. All voltage sources are non-ideal. There is the ideal voltage source or current source does not exist. And that is why, along with this current source that we have defined as Gm times VGS, you will see a parallel resistance to it. Again, remember that current sources have a parallel resistance to it. Voltage sources have a series resistance associated with that voltage source. So I think in some of your earlier homeworks, some of you had made the mistake that when you were talking about a current source, you still took a series resistance. That is not right. That is not the model of a voltage source or a current source. If it is a current source, it needs to have a parallel resistance. If it is a voltage source, it needs to have a series resistance. Okay? And that's the only reason why you can place two voltage sources in series, but you cannot put two voltage sources in parallel, right? Just like remember your flashlight, you put your batteries in series, right? You cannot put the batteries in parallel in a flashlight. Similarly, when you talk about currents, you cannot put current sources in series. Then you don't know what is the total amount of current flowing through that series branch because your KCL will be violated. So when you have current sources in parallel, it is fine because parallel currents can flow through two different branches. And that's the reason why whenever you're talking about this resistance will also be in parallel because there could be some additional current flowing through that resistance, and that is possible. All right, so this is the linear equivalent model of your MOSFET, of the N-channel MOSFET that we just discussed. So your current is flowing in this direction. You want to find out what would be your drain to source voltage, eventually the output voltage between drain to source. That's something you are interested in finding. If this is the direction of the current, and if you do not have any resistance, any additional resistance connected at this point, okay, if you do not have this RD resistance, for example, what you only have is this R0 resistance in parallel with the current source. So your current is flowing like this in this loop, okay? So what is the drain to source voltage? That will be minus of Gm times VGS, that's the current, times RO. And why minus? Because your drain voltage is here, which is, since we are talking about drain to source voltage and not source to drain voltage, your drain terminal should be considered as the positive terminal because you're talking about drain to source voltage. And your source terminal is the negative terminal. Because the current is flowing in the opposite direction, your VDS is minus Gm times VGS, that's the current, times RO. That's the resistance that you have between the drain and the source. Okay, so that's your VDS. And what would be your VDS over VGS? So drain to source voltage divided by gate to source voltage will be minus Gm times RO. And this is called the intrinsic gain of a MOSFET. That Gm is an intrinsic property of a MOSFET. RO is also an intrinsic property of the MOSFET. Right? Gm gives you the how much amount of current you should expect if you are applying a particular amount of voltage at the input. RO tells you that what is the non-ideality in the small signal model of the MOSFET. That you do expect a current at the output, but of course it's a non-ideal current source, so you will have an RO which is the output resistance of the MOSFET. So GM and RO both are properties of the MOSFET, and the multiplication of those two gives you the intrinsic gain of the MOSFET. That's the maximum gain that you can expect out of any MOSFET-based circuit. And what is RO? Again, if you go back to these plots of ID versus VDS, you know that the slope of these ID versus VDS plots are 1 upon RO. So that's where your RO comes in, and we already proved the equation of RO will be equal to 1 upon lambda ID. That's the value of your output resistance. That lambda is the channel length modulation parameter, because you know that ideally these slopes should have been 0, or the resistance should have been, output resistance should have been infinite. But instead, you do not see a 0 slope, or you do not see an infinite output resistance. What you see is 1 upon lambda ID. Lambda is called the channel length modulation parameter, and it will be given in your problems, homework problems, or exam problems. And ID is the point, bias current, at which you have the transistor DC bias, that how much current is flowing in DC condition through the MOSFET. That's your ID. So RO is given by 1 upon lambda ID. So if you need to find out RO for the transistor in any of the problems, this is how you find it out. And we proved it in the previous class that why your RO is equal to 1 upon lambda ID. All right. So minus GM times RO is the intrinsic gain of the transistor when the transistor is in this configuration. And we'll discuss this configuration in a little more detail in our next classes. This is called a common source configuration. So some of you may have heard about different configuration of an amplifier, a MOSFET amplifier. It could be common source, common drain, or common gate. These are the 3 configurations that we generally see for a MOSFET. And it depends on the 3 terminals. You have the gate terminal here, you have the drain terminal here, and you have the source terminal here. Whichever of these 3 terminals is connected to a common reference. For example, in this case, the source terminal is connected to a common reference, which is ground. That is the reason why this is called a common source configuration. And in a common source configuration, you apply your input at the gate and you observe your output at the drain terminal, while your source terminal is the common terminal or the reference terminal. So this is called common source. We'll look into each of those configurations in more detail in our future classes. But right now, just think about it as a particular configuration, which is called a common source configuration of the MOSFET. All right, and in the common source configuration of the MOSFET, the intrinsic gain is minus GM times RO. But what we were looking at in the previous page was that the gain is minus GM times RD and not minus GM times RO. Why is that? That is because here you had an additional resistance between the drain terminal and the VDD. Okay, so if you go back to the next, if you consider this small signal model or the linear equivalent model of the MOSFET, what you now have is one additional resistance between the drain terminal and the VDD. So you have one additional resistance between the drain terminal and the VDD. Now remember, in terms of AC signals, your VDD is a ground, right? VDD is a virtual ground. Your supply is a virtual ground when you're talking about AC. Why is that? Because at your supply, do you have any kind of fluctuations in the voltage? Ideally, no, right? If there is noise, you'll have some fluctuation, but we're not considering that at this point. But at your supply, ideally, there should not be any AC voltage. Your AC voltage should be at your input or output, not at the ground or at the supply. So in terms of your AC voltages and currents, your supply is a virtual ground. So the AC voltage at your supply is equal to 0. If your AC voltage is equal to 0, at any point, that point is called a virtual ground, because AC voltage is equal to 0, that's effectively an AC ground. So your supply is an AC ground. Even though it's a DC 5 volt or a DC 10 volt, DC 3.3 volt, does not matter. In terms of AC, it's a 0 volt. Your supply is called an AC ground, and that will be true for any circuit. Whenever you have a supply, your supply will be an AC ground. because there is no, ideally there should not be any AC fluctuations in the supply. And if that is true, one terminal of this resistance will be connected to the drain. The other terminal of this resistance will be connected to the supply. But you know that the supply is an AC ground and your source is also an AC ground. The source terminal is an AC ground. The supply terminal is also an AC ground. Correct? So these two terminals are actually connected together in terms of your AC. One terminal of the resistance is connected to the drain. The other terminal of the resistance is connected to the supply. And because the supply is an AC ground, you can connect these 2 points together. You already knew that the source is grounded. And your other terminal of the drain resistance, that's also grounded in terms of AC. And that's why you can connect these 2 points together. So now what do you have? You have this RO and RD. RD is the drain resistance, the physical resistance that you had connected at this point. This is RD, the physical resistance connected at the drain terminal between the drain and the VDD. So because these two resistances are in parallel now, so your overall gain, the intrinsic gain was GM times RO, but the actual gain becomes minus GM times RD in parallel with RO. Because these two resistances are now in parallel. So the voltage that will be developed across the resistance will depend on the parallel value of these two resistances. Correct? Everyone agrees? Now, if your RO is very, very high as compared to your RD, usually RO is in the range of hundreds of kilo ohms, maybe even a mega ohm, but definitely in the range of hundreds of kilo ohms. If your RD is in the range of, let's say, 1 kilo ohm or so, 1 kilo ohm is much, much smaller than 100 kilo ohms. So when you have a 1 kilo ohm resistance, which is your RD, in parallel with a, let's say, 100 kilo ohm resistance, what would be the effective parallel combination of those two resistances? It will be almost equal to the smaller resistance. In this case, which will be equal to the 1 kilo ohm RD resistance. That's why whenever you have this RD, if this RD is much smaller than RO, your gain becomes minus GM times RD. If you want to have the exact form of the equation, it's minus GM times RD in parallel with RO, which is shown here. But because in most cases RD is much, much smaller than RO, your equation will be minus GM times RD. Now, of course, in your exam, if you see your RD is 100 kilo ohms, your RO is also 100 kilo ohms, you cannot neglect one or the other. In that case, you have to take the parallel combination of RD and RO. But if you see that your RD is 1 kilo ohm, RO is 200 kilo ohms, then of course you can ignore RO because the parallel combination of RD and RO will be equal to RD. Any questions at this point? All right. So that's the equation of gain in very simple terms for this common source amplifier, that it will be minus GM times RD, or in more stricter terms, it will be minus GM times RD in parallel with RO. All right. Now, what I want to do today is that because your homework 4 submission is due on this Wednesday, and homework 4 is also very important for your exam number 2, I'll discuss a few questions which are very similar to homework number 4. In fact, these were the homework questions from last year. Of course, the values are different, but the way the analysis should be done will be very similar. So I'll go over some of this analysis so that it helps you in solving homework number 4. If you have not already done that, or you have not already submitted that, this will help you in understanding how to solve homework number 4 questions. Okay, so here, of course, the numbers will be very different. So don't take this as your answers of your homework number 4, but this will give you the thought process or the methodology to solve these questions that are given or that are asked in homework 4. So the first question, you have this MOSFET, you have a plus 7 volt in VDD, and you have minus 7 volt in VSS. Your gate is grounded. Now, someone asked in the last class that because this gate is grounded, do I have a VGS equal to 0, and is the MOSFET is in cutoff? The answer is no, the MOSFET is not in cutoff, because even though the gate is grounded, the source is not grounded. So the definition of cutoff is that your VGS has to be less than V threshold. In this case, even though your gate is 0, your source could be at a relatively negative potential, so that your VGS, the voltage between your gate and source, that could still be more than your threshold voltage. So it is not true that the MOSFET is in cutoff. The MOSFET is, as you will see, will be in fact in the active region or the saturation region. Okay, so the first question is that, assuming your VT is 1.1 volt and K, which is equal to K prime times W over L. So remember that whenever K is given, that is equal to K prime times W over L, or mu time, in this case it's a MOSFET, N-channel MOSFET. So I'll write mu N times COX times W over L. That is given as your K. Okay. That is 25 milliampere per volt squared. Now you need to choose the values of RS and RD so that your ID is equal to 2 milliampere and VD is equal to 2 volts. How to solve this? For RD, it is very easy. The resistance that is connected at the drain, you know that one of the terminal is 7 volts. In the question, it is asked that the other terminal has to be 2 volts. VD is this point that is given as 2 volts. Right? If this point is 2 volt, this point is 7 volt, and you know the current flowing through it is equal to 2 milliampere, you can definitely find out the resistance. No question about it. Right? RD is equal to 7 minus 5 divided by 2 milliampere, that will give you 2.5 kilo ohms. Of course, the numbers are different in your homework form, but this is the way you should solve it will be very similar. Next, assuming, of course, you still need to find out RS, and finding RS is a little bit more difficult than finding RD. How do you find out RS? You know that for finding out RS, for finding out the voltage at this point, you need to have an idea about how much VGS do you have. You know your gate voltage. If you can find out what is your VGS, you can find out your VS, right? Gate voltage is known, gate to source drop is known, then you can find out your VS. How to find out the gate to source drop? For that, you need to find out what is the overdrive. V overdrive is equal to VGS minus VT. So if you can find out your V overdrive, you already know your VT, the threshold voltage. So in that case, you can find out what would be your VGS. And if you can find out your VGS, you can find out what will be your VS. Okay. Now, to find out your V overdrive, what you are going to do is that you're going to assume that the MOSFET is in active or in saturation region. And you know the equation of ID when the MOSFET is in active or saturation region. That ID is equal to K over 2 times V overdrive squared, which means your V overdrive is equal to square root of twice ID divided by K. So just from this equation, ID equal to K over 2 times V overdrive squared, you can write down V overdrive is equal to square root of twice ID divided by K. Now you already know what is your ID, and you know what is your K, so you can find out what is your overdrive voltage. And if you can find out your overdrive voltage, then you can find out what would be your VGS. Because you know your gate voltage is equal to 0, you can find out what would be your source voltage. Now, one thing that we did not talk about yet is that why did we assume that the transistor is in active region? That is because your VD right now is at 2 volts, your VG is at 0 volt. So what is your VGD? What is your gate to drain voltage? Gate to drain voltage will be equal to minus 2 volts. And the equation for the transistor to be in active region is that your VDS should be more than, or let's say greater than equal to, for now I'll just put the greater than sign, or it's actually greater than equal to VGS minus VT. That's the condition for your transistor to be in saturation. Now, on the left hand side, it is VDS. What is VDS? VDS is VD minus VS. So VD minus VS has to be greater than equal to VG minus VS minus the threshold voltage. Now you have the VS both on the left side and right side, so you can just ignore it. Your equation will become VD should be greater than equal to VG minus VT. Okay. In other words, you just take your VD on the right hand side and VT on the left hand side. What it would mean is that your VGD has to be less than equal to VT. So that is another way you can represent the equation of your active or saturation region. That if your gate to drain voltage is less than VT, then it means that you satisfy the VDS greater than VGS minus VT equation. So in this case, your gate to drain voltage is minus 2 volts, which is of course less than your threshold voltage. That means you are in the active region. And that's the reason why we applied the equation of your active or the saturation region. Okay. So you can find out what would be your V overdrive. You know your VGS is equal to VT plus V overdrive from this equation. Because your V overdrive was VGS minus VT, your VGS is equal to V overdrive plus VT. So if you can find out what is your V overdrive, in this case it is 0.4 volts. Now of course, you could ask mathematically, I could have plus minus 0.4 volt here because you're taking a square root of a positive quantity. So your V overdrive could have been plus or minus. But having a negative V overdrive does not make any sense over here, which means that the transistor will be in cutoff. Right? What is V overdrive? V overdrive is VGS minus VT. By how much amount your gate to source voltage is more than your threshold voltage. If that is a negative quantity, it does not make any sense because then your transistor is in cutoff. You want your transistor to be in non-cutoff region, it needs to be on, and it needs to be in the active region. So that's why you're considering only the plus 0.4 volt number and not the minus 0.4 volt number. Okay. So your VGS will be 1.1 plus this 0.4 volt, which will give you this 1.5 volt number. So that is your gate to source voltage. Of course, your gate voltage is 0. So your source voltage has to be minus 1.5 so that your VGS is 1 plus 1.5, right? So your VGS is plus 1.5 volt, your gate voltage is equal to 0, which means your source voltage has to be minus 1.5. Now you can find out what is your RS. Your RS is basically the source voltage minus VSS. So the difference between the source voltage and VSS divided by the current that is flowing through RS. So what is your source voltage? That is minus 1.5. What is your VSS? That is minus 7. So the voltage drop across RS is basically this 5.5 volt, which takes this minus 1.5 voltage down to minus 7 volts. So that is the total amount of drop across RS, which will be equal to 5.5 volt. What is the current that is flowing through RS? That will be the same current that is flowing through this entire device. So ID is equal to 2 milliampere. The drain current is 2 milliampere. The source current has to be equal to 2 milliampere because there is no other way for that current to go. It's KCL, right? If there is a certain amount of current coming into the device, the same amount of current has to go out of the device. So if the drain current is 2 milliampere, the source current also has to be exactly equal to 2 milliampere. Now you solve that, you get your RS to be equal to 2.75 kilo ohms, some number, but yeah, you get the point how to solve this particular question. Okay. Now you can find out what is the second part is that assuming your ID to be equal to 2 milliampere, what is the largest value of RD? What is the largest value of the drain resistance RD that you can have for which the MOSFET stays in the active region? So you need to find out what is the largest value of RD for which the FET stays in the active region. Now, imagine this, that as you are increasing the value of RD more and more, you want to find out the largest value of RD for which you are still in the active region. So as you are increasing the value of RD, if your ID is still 2 milliamperes, if the ID is fixed, the voltage drop across RD keeps on increasing and increasing. Right? The voltage drop across RD will keep on increasing as the value of RD is increasing, which means the voltage drop across the rest of the circuit will keep on decreasing. And of course, because RS is fixed and your current is fixed, the voltage drop across RS will be fixed, which means that the voltage drop across the MOSFET will keep on reducing as the voltage drop across RD keeps on increasing. The total voltage drop has to be equal to 7 volt minus of minus 7 volt. So the difference between VDD and VSS is 14 volts in this case. And the total voltage drop across the two resistances and the MOSFET has to be equal to 14 volts according to KVL. Okay. Now, if one of those voltages increase, the other voltage has to reduce. And if your VDS is reducing, as your RD is increasing more and more, if your VDS is reducing, at some point, this condition will be violated. You needed your VDS to be more than VGS minus VT. This condition will be violated at some point as your VDS is reducing. VDS will not remain more than VGS minus VT at some point of time, and you're asked to find out what is that point in terms of the value of that resistance RT. Now, to solve that, you need to find out what is the minimum value of VD, what is the minimum value of your drain voltage to be in the active region. Now, if you consider your ID versus VDS characteristic, so let's say your y-axis is ID, your x-axis is VDS. If you consider your ID versus VDS characteristic, the saturation region starts when your ID becomes almost saturated, right? So this is the point. This is the minimum value of VDS that you need to have. This is the minimum value of your VDS that you need to have for your device to be in saturation. And at the same time, that is the maximum value of your current that is achieved in the triode region. And you already know that this value is achieved, this inflection point is achieved when your VDS is equal to VGS minus VT. So this point is VDS equal to VGS minus VT. Beyond that, your VDS will be more than VGS minus VT, which means you are in saturation region. And below that, your VDS will be less than VGS minus VT, which means that you are in the triode region or the linear region, right? So this point where the transistor changes from the triode region to the saturation region, at that point, you have VDS equal to VGS minus VT. So that is the value of your VDS min for the transistor to be in active region. So this is the VDS min, minimum value of your VDS, so that your transistor is still in active region. This is also called VD-SAT. That what is the VDS that you require for your transistor to be in saturation. So this is just a terminology that whenever you encounter this term as VD-SAT, it means the VDS min for which that your transistor is in saturation region. So it signifies this point where your VDS is equal to VGS minus VT, and that VDS we call as VDS min. And in some books, you'll see that it is mentioned as VD-SAT, that is the minimum value of VDS for which your transistor will be in saturation. So all of them mean the same thing. So VD, what would be your VD min so that you are in the active region? Okay, so you know that VDS min is equal to VD-SAT, but VDS itself is equal to VD minus VS. Correct? VDS is itself VD minus VS. So if you are only trying to find out what is the minimum value of VD for the transistor to be in saturation, that would be your VD-SAT plus VS. Because VDS minus VS is equal to VD-SAT. So VD minimum is equal to VD-SAT plus VS. Okay. Now you already know what is the value of your VS, that is minus 1.5 volt. You already know what is the value of your VD-SAT. VD-SAT is equal to your VGS minus VT. You already found out what is your VGS minus VT, or you already found out what is your V overdrive. V overdrive is equal to VGS minus VT is equal to 0.4 volts. So you just put that value of 0.4 volt over here and minus 1.5 volt for your VS. So you get your VD min for your active region to be equal to minus 1.1. That is the minimum value of your drain voltage. That is the minimum value that you can have at that point so that your transistor is still in saturation. In the previous part, in part A, your VD was 2 volt. If your VD drops to minus 1.1 volt, still the transistor will be in saturation. But if it drops any further, the transistor will go out of saturation. The transistor will be in triode region. Okay. Now you are asked to find out what is the maximum value of resistance that results in that VD of minus 1.1 volt. So you already know your VDD, you already know the other point of the resistance. So the resistance, remember that the top terminal was connected to VDD and the bottom terminal was connected to VD, and you knew that the current through the resistance was 2 milliamperes. Now in this case, your VDD is 7 volts. Your minimum value of VD for which the transistor is still in saturation is equal to minus 1.1 volt, and your current through the device is 2 milliamperes. So you can find out what is the maximum value of that RD resistance that results in the scenario, results in the condition when your VD reaches your VD min. Okay. So that's how we are going to solve part B of this problem. Question number 2 for your homework had a diode connected MOSFET. Now this is called a diode connected MOSFET. Why is that? Okay. And the solution process will be very similar to what you have in this particular question number 1, and we'll go through that in a little bit more detail right now. But what I wanted to mention before that is that this particular configuration of the MOSFET is called a diode connected MOSFET. Why is it called a diode connected MOSFET? You know what is the property of a diode? That the diode lets current flow in only one direction. The current can, in this case, the current can flow in from left to right, but current cannot flow from right to left. That's the property of a diode. In this case, what is happening is that as you are connecting the gate of the MOSFET to the drain terminal of the MOSFET, if your voltage at this point is more, so let's say in this case you have connected your VDD at this point, and let's say you are connected a small value of Vs at the source terminal. If your voltage at the drain terminal is more than the source terminal, then you'll get a current flow through this device. Why? Because your drain is connected to the gate. Your drain is so VDS is actually equal to VGS in this case, right? Because your drain is connected to the gate, so VDS is equal to VGS. Now, assuming that your VGS is more than your threshold voltage, your gate to source voltage is more than your threshold voltage, which will be the case because your drain is at a very high voltage, right? If your drain is at a very high voltage, there is a very high probability that if your source voltage is, in this case, let's say your VT is 1.1 volt. So as long as your source voltage is less than 4.9 volt, your transistor will be on, right? It will be out of cutoff region. But at the same time, remember that VDS equal to VGS, which means that VDS will be always greater than VGS minus VT. So in this configuration of the MOSFET is always in saturation. You don't even need to test. In the previous case, you had tested whether the MOSFET is in saturation or not by looking into the VDS and VGS values. But in this case, you don't even need to test it out because your VDS is equal to VGS, which means that VDS is always more than VGS minus VT. VT is always a positive quantity for an in-channel MOSFET, right? So if your VDS is, let's say, 4 volts and your VGS is equal to 4 volts. So 4 volt is always equal to 4 volt minus 1.1, right? So you don't even need to test anything in this case if the transistor is connected like that, which is called a diode connected configuration. Why is it called a diode connected configuration? Now let's just assume that you reverse the polarities of the voltages, that you provide a higher voltage in this case. Let's say you provide 6 volt at this point and you provide 0 volt at this point. Okay. You know that for an in-channel MOSFET, the current flow is always from drain to source. So if you are applying a higher voltage, wherever you are applying a higher voltage, so let's say the in-channel MOSFET is drawn like this. If the current flow is from drain to source, that means a positive voltage is applied here and a negative voltage is applied here, right? That's how the current flow will occur through the in-channel MOSFET. Now let's just assume that you reverse the polarities of when you are connecting it to the MOSFET, that you have a positive voltage at this point and a negative voltage at this point. What that will do is that the current has to flow from the positive voltage to the negative voltage, which means that your current will flow in this direction, which means that this will become the source and this will become the drain. So source and drain terminals in a MOSFET are reversible. It depends on where you are applying the positive voltage and where you are applying the negative voltage, or where you are applying a higher voltage and where you are applying a lower voltage. In whichever terminal you are applying a higher voltage, that becomes the drain terminal for the N-channel MOSFET. Whichever terminal you are applying a lower voltage, that becomes the source terminal for an N-channel MOSFET. Because the current always has to flow from drain to source. Current cannot flow from source to drain for an N-channel MOSFET. The electrons flow from source to drain. If electrons flow from source to drain, current will have to flow from drain to source. Now, just a quick note about why we are calling it a diode connected MOSFET. If you're reversing the polarities, let's say this is the higher voltage and this is the lower voltage, then this will become the drain and that will become the source. If your gate and source terminals are connected together, your VGS will be equal to 0. If your VGS is equal to 0, that is definitely less than the threshold voltage, and the transistor will not turn on. If the transistor cannot turn on, there cannot be any current flow in this direction. So even if you reverse the polarities, you do not expect the current to be reversed. And that's why it's called a diode connected configuration, because it is very similar to diodes, where you expect the current to flow in only one direction and not in the other direction. So that's the reason why it's called a diode connected MOSFET. Now, how you'd solve it? It's very similar to your previous question, that you need to find out the value of R to get an idea about this point. So for that, you'll use the same equation, the overdrive is equal to square root of twice ID over K, and you'll take the positive value of that square root, not the negative one, because you want a positive V overdrive for the transistor to be on. And you just solve the value of VGS, and from that, you can find out what would be the value of RS, okay? And if the value of R changes to something else, you can always find out what would be your ID and what would be your VS. And question number 3, again, very similar. It's just that at the input side, you have two RG1 and RG2. These are the two gate voltages. And you have to choose the gate voltages in such a way that VG becomes 4 volts. So VG becomes a particular voltage. So you need to choose these two voltages in a particular way so that you get a particular voltage division between VDD and ground. So that's the only difference of this question, question number 3, as compared to your question number 1. So this is how you're going to solve the methods. I'll just stop here so that in the recorded video, you can look at how this has been solved, and you can use the same method to solve your homework number 4. Okay. Question. This file I'll not post, but I'll post a video. Yeah, because you can see whatever has been done in the video, because I'm just pausing in this particular question so that you can take a look at it, what has been done in the solution. Okay. Yeah.